It's Mauro Bianco. I work at CSCS, and I'm going to talk today about profiling complex parallel application using VampirTrace. For complex parallel applications, we mean C++, heavily templated codes using MPI and CUDA in them. The main motivation for this work is the GCL, which is generic communication layer or library, depending on your taste, and which is a flexible interface for LO update operations. LO update is an operation used by many scientific codes and applications that uses domain decomposition. In our case, we're working with regular grids, 3D arrays, and we need basically to update the borders of these 3D arrays with neighbors MPI tasks. And this operation is implemented with the GCL. We have additional requirements and constraints. The idea is that this code should work on hybrid architecture, so CPU and GPUs, and should allow us to customize memory layout, since GPU and CPU might have different best layouts for a given application. We have also to handling custom padding on the dimensions because of alignment issues that you can have on the GPUs and on the CPUs. And of course, that you have also to be able to deal with different element types, so vectors of integers, double floats, and whatever structures the user wants to use. To do this GCL, we had to use basically C++, which is the only language that allows to reach good performance and flexibility at the current state. So, give you an example of what the code looked like. We basically define pattern, and which is an LO exchange dynamic. In this case, well, the name is not really important. We specify the layout in the storage, the layout of the computing grid, so we can also deal with different orientation of our computing grid, the element type, the number of dimensions, where the data is, which is in the GPU, and how to pack and unpack data. This is what we're going to talk later. So we create the pattern. In this case, it's called LO exchange, and with some period type, so we can have wraparounds our dimensions, which are arbitrary and runtime decided. And you have a communicator, basically, an MPI communicator. Then we describe our structure, which is basically how many halo points we have at the left, how many points we have at the right, how long is our inner region, and how long is the full dimension. And this for all the dimensions that we have in our 3D array. Then we set up our pattern. We pack. In this case, we pass 3 pointers, which are which basically points to data on the GPU, and then we run LO exchange, and then unpack the data back into the GPU pointers. This exchange call can be split into start exchange and wait to be able to implement also a split phase communication and latency hiding tricks. So this is how the code looked like, and we basically, what we do is the packing and unpacking part is very important. On the CPU, we basically loop on the neighbors, and then we collect the data in a cache-friendly way. So we know the layout of memory at compile time as a type information, so we can basically get the data in the best efficient way. And then we can also pack different neighbors in parallel using OpenMP. This is not always a good idea, though. Then on the GPU, we do something different. And we basically have up to 6 CUDA kernels to pack data for different neighbors. So each neighbor, each task can have up to 26 neighbors, but we only have 6 CUDA kernels to pack data. And so this actually allows us to compress the computation more than a simple MPI implementation. What else you can do here is that, okay, one data field is packed at a given time. So before we had 3 pointers, 3 data fields. We first pack the first one, then the second, then the third one. So we have 6 times 3 kernels running, which is, I guess, 18. So how do we do this 6 packing, these 6 kernels? So suppose you have a 3D array, and we can see here the 3D structure. We can imagine that this is your logically out of memory, and we take a surface of this cube, and we say, okay, we need to collect data to 9 neighbors, and you have a single kernel who basically unpack the data and store into some buffers. Then for the side, we have only 3, because we already manage the vertical columns. And then for the last one, we have a single surface to exchange. So totally is 6 kernels. One kernel per surface. There are 2 surfaces, one in the front, one in the back. So there are 6 kernels that does this operation. Unpacking works in the same way, only that, of course, the data has to be placed on the outside of our 3D array. Any questions? Everything okay? Yeah, the corners are smaller data. Yeah, it's actually constant amount of data. It's typically hello width cube. This one is slightly bigger. This one is slightly bigger, and this one is the largest, which is also an issue because you have to exchange different sizes of messages. But yeah, the corners are much smaller than the rest, and they typically go with the MPI eager protocol. So let's see the scalability of this guy. GCL. If we take a 250 by 250 by 250 3D arrays with 3 elements of all around, and all the dimensions are wrapped around, so it's like a torus communication, and we can see that if we are running on 48 processes on an XK7, we can see that packing time and unpacking time are actually larger than the exchange time on the CPU. While when we run on the GPU, the packing and unpacking is basically nothing. And the exchange time is more or less the same, even though sometimes it's faster on the GPU. And it's faster on the GPU because Cray was able to implement a very good strategy to get the data out of the GPU very quickly. When we move to 256 processors and 1 per node, then we can see this, that the GCL scales quite well. And again, packing and unpacking time are much larger than the communication time. And also on the GPU, scalability is quite good in here. Well, we tried also on other machines, like an iDataplex, and we have similar results, even though this MPI implementation is slightly slower on the GPU, but also because we have older GPUs in there. Well, we tried also on XC30, but that's not really the point of the presentation. So what do we want to do now is to show we had some issues, like synchronization issues and for the MPI tasks and for the CUDA kernels. So we had to run some profiling tool to understand what was going on. And a tool that we are using here, CSCS, is VampirTrace. The only problem is that when you run on C++, when you work on C++ with a lot of templates, and your inlining is essential to get some good performance, well, it turns out that VampirTrace does a very bad job if you let it do it automatic things. What VampirTrace and other tools do is basically a source-to-source translation. They take the functions in your code and they put calls before calling the function and after calling the function. They say, okay, this is the time the function is taking, this is the timestamps or whatever. But if your code relies a lot of inlining, this instrumentation code is actually disrupting all the potential for your performance. So what do you have to do if you have heavily templated code? Well, you just have to say to VampirTrace, just do not do anything. Don't instrument. And this is the option that we have here, which is VT instrument manual in the compile line, in the VTCC compiler. And then we can say, well, you can also monitor MPI tasks, though, because the MPI calls are always, in some sense, runtime calls. So they're always, traced. In this way, let's say the code, VampirTrace will not show much information. It will show you MPI calls, and will show you also CUDA kernels, but not any other function in your code. And if you are lucky, there are not many functions in your code anyway. So what you have to do to enable then the GPU profiling, then you have to set the VT GPU trace with some options. It's like kubT for the low-level driver interface. Runtime, we want to monitor the kernels. We want to monitor mem copies. You want to monitor concurrent, so many kernels launched at the same time. And then you want to set some CUDA trace buffer to collect data to some number that doesn't break your code. There are other variables which are more standard, and I'm not going to talk about them. So let's see some real demo example with Vampir. So when you run the CPU version, so the one that doesn't use the CPU, what you see is basically we are here running a benchmark which have a 300 by 300 by 300 with 5 elements of Halo all around, and we have 8 MPI tasks. And what we want to do is just do this Halo exchange, and then check if the data arrived correctly. So the green part, it's all the data it's all the computation that takes to write the data, and then check that the data arrived right. And then these arrows here are basically the 5 experiments that I'm running. So we can zoom in, and you typically have to do some zooming yourself, and we can see what's going on here. Okay, here to here. And VampirTrace gives you the information about this code, this section of code. And you can see the green part here is packing. The green part here is unpacking. And there are some, of course, some synchronization issues, some load balancing issue. And then here there is the communication part. And as you know, with VampirTrace, you can click on an arrow, and you can see a lot of information about how much data you are exchanging and how long it took. But this CPU version is very simple. It just go there, pack the data, run the MPI exchange, then unpack the data back. Now we want to do this on the GPU. If you want to do this on the GPU, well, you have to get this one. This is already zoomed in the same region, basically, that we had before. And what we can see is slightly more complicated picture. Well, if you go here and see, for instance, what happened on the CPU, we can see up here the time that it takes, 0.32 seconds for this section of the code. Now, when we move to this one, we have 93 milliseconds. Well, which is already a good step forward, because the packing and packing time is basically nothing now. But then we can see many other information. We are using Cray MPI, which is able to do GPU-aware MPI communications. Basically, you give the point to MPI, the pointer to GPU data, and he will deal with everything. In this case, we're not using this. This is just to see what happens if you implement things in a not so smart way. So in this case, we run our kernels. Now we run our 18 kernels in three different streams. We can also zoom in and see our streams, our kernels run for packing, and the same would be for unpacking. Then after we packed all the data, we copy the data from the GPU to the host, and then we call the MPI exchange. As you say, it's a very naive implementation. But this already is like 3 times faster than doing on the CPU. And here we can see the mem copies that we are doing. Sorry, this one are the mem copies that we are doing to copy the data out. And here we have similar calls for copying back. And then we have the unpack kernels that put the data back to the proper place. All the arrows here are all the MPI communications. Now we want to do something smarter. We want to use the GPU-aware abilities of our MPI implementation. And the picture changes quite a bit, quite a lot. Now we are using a single stream for packing and unpacking. This is also a GCL thing that you can set. You can say how many streams you want to use to pack and unpack kernels. Unpack your inputs and outputs. In this case, well, we can see, okay, we have a single stream for packing. And this is one of the reasons why we actually were running this kind of experiments. You can see that these 2 streams are not created by me, by GCL, but they're actually created by Cray. So Cray uses additional streams to pack and pack data. And this was creating issues because we were not synchronizing, because we were basically using mVampIch first. And mVampIch uses stream 0 for doing everything. And so it was automatically synchronized. But Cray uses other streams. So our IL exchanges were not correct all the times. And thanks to this tool, we were able to find out this fact. We also could find out other things. For instance, that all these arrows here from and to GPUs, and we can see how much data they are exchanging. It's like 512 kilobytes. So all these arrows here are exchanging 512 kilobytes of data. And this is the magic size Cray chose to have a good pipelining. Pipelining means while I'm copying data out of the GPU, I'm actually sending some other chunk to the other side. And so I can basically pipeline and get the whole bandwidth that I could. While before we were copying the data out and then exchanging, we were basically using half of the bandwidth that we had available. And in fact, you can see in the execution time that this is 55 milliseconds instead of 94. So it's almost half the time that you can in our naive implementation. Well, with this tool, you can also, with GCL, you can choose how many streams you want to use. You can use up to 6 streams for packing and packing. Basically, one stream per surface of our 3D array. And you can see what happens here, right? I mean, this, again, we can see that Cray is using 2 additional streams, the stream 8 and 9. Last pointer, okay, 8 and 9. And then the other from 2, from 2 to 7 is basically our streams. And you can see is that even though the streams are run in parallel, are basically asked to run in parallel, they don't run in parallel. There's only some little tail effect here. And the reason is that there's enough data to keep the GPU busy, so it cannot really share the GPU among different CUDA kernels. So in fact, you don't see any advantage of using multiple streams in this case. And in fact, the time is basically 1 millisecond less than before, but this is basically noise, and also the fact that I'm zooming into this area not very precisely. So what we can see here is really the behavior of your communication with the GPU and among other MPI tasks. So in conclusion, profiling C++ with templates is tricky anyway. It's always complicated. Long function names, very difficult to understand, and also profiling in this case is not perfect because the instrumentation of the code should happen after compilation instead of before the compilation. But this will change the old workflow that the tool should follow to instrument the code. So if you add GPUs and MPI, this helps. You can get some information out of it. If there was not MPI, no GPUs, basically VampirTrace would be totally useless for this case. But in this case, we can at least trap some of these events. We have to reverse engineer a lot of stuff to find out what options to use, and and also why our application was not working, how the MPI implementation worked, etc. But this, this was a good exercise, and my advice is keep instruction on the wiki, because you will forget this after 2 hours, and that's it.